A very warm welcome, bachon. Today, we are tackling a very interesting topic from wave optics, interference. I promise, we will make it so simple that you not only understand it for your exams, but you'll remember it for life. Chalo, let's get started.
So let's begin with something you've all seen, right? A simple soap bubble, and it shimmers with all these beautiful rainbow colors. Have you ever wondered where these colors come from? I mean, the soap water itself is clear, it's transparent. So what's going on here?
Well, the answer is not some chemical magic. It's a beautiful phenomenon of physics, and today we are going to understand it completely. You see, the secret is hidden in the very nature of light.
Let's just call this our little soap bubble mystery. And you know what? By the end of this session, you'll be the one explaining the solution to everyone else.
Okay, so to understand how light does this, which can be a little tricky, let's first think about something much simpler that we can all picture in our minds, ripples in a pond.
Just imagine, you drop 2 stones into a still pond at the exact same time. 2 sets of circular ripples start spreading out. Now, the really interesting part is where they meet. When the top of one wave, its crest, meets the crest of another, they add up to make a much bigger wave. But what happens when a crest meets a trough, the bottom part of a wave? Well, they just cancel each other out, and for a moment, the water becomes perfectly flat right there.
And here's the big idea, y'all. Light behaves in exactly the same way. Why? Because light itself is a wave. This idea of waves adding up or canceling each other out, this is the core idea of interference. And light waves, they do this all the time.
Okay, so the water ripple idea is clear in your mind, right? It's a fantastic way to understand the concept. But now, for the important part, let's see how we write this perfectly for our exams to get full marks.
For your exams, this is the definition you need to write. Interference is the phenomenon of redistribution of light energy when 2 or more coherent light waves are superposed. Now, superposed is just a fancy word for overlap. And that very important word, coherent, simply means the waves are perfectly in sync, just like our 2 pebbles being dropped at the exact same moment.
So this overlapping gives us 2 possible results. On the left, we have constructive interference. Just think of this as crest meets crest. The waves help each other. They build each other up, creating a bright spot. This happens when their path difference is a whole number multiple of the wavelength, or n lambda. And on the right, we have destructive interference. This is our crest meets trough. The waves cancel each other out, creating a dark spot. This happens when the path difference is an odd half multiple, or n plus 1/2 lambda.
All right, now let's see how this idea creates that famous pattern of bright and dark bands, we call them fringes, that we see in the classic Young's double slit experiment.
The logic is actually very simple. You take light from 2 very narrow, coherent sources, the 2 slits, and you let it spread out and overlap on a screen. Now, wherever the condition for constructive interference is met, that path difference of n lambda, you get a bright band. And wherever the destructive condition is met, path difference of n plus 1/2 lambda, you get a dark band. And this just repeats, creating that distinct pattern of alternating bright and dark lines.
You know, theory is good, but nothing makes a concept clearer than solving a problem, isn't it? So let's apply this with a very simple numerical example, exactly the kind you can expect to see in your exam. Okay, let's look at the data we have. The wavelength, lambda, is 500 nanometers. The distance between the slits, small d, is 0.5 millimeters, and the distance to the screen, capital D, is 1 meter. We use the straightforward formula for fringe spacing. Beta is equal to lambda times d divided by d. Now the most important step here, the place where students make mistakes, is to convert everything into meters before you calculate.
And once you do the calculation, it's very simple. The answer for the fringe spacing, that's the distance between one bright fringe and the next one, is exactly 1 millimeter. See? It's all about knowing the right formula and being really careful with your units.
All right, now for a very important part. I am going to tell you about the silent killers. These are the common mistakes and wrong ideas that even very bright students make in exams, so please pay close attention.
First mistake. A lot of students think that a bright fringe only happens right in the center, where the path difference is 0. But that's just the central bright fringe. The correct idea, as you see on the right, is that a bright fringe will form anywhere the path difference is a whole number of wavelengths, so 0 or 1 lambda, 2 lambda, and so on. A difference of 1 full wavelength just means the 2 waves are perfectly in sync again.
And now for the biggest silent killer of all.
This is a mistake I see in so many exam papers. It's about the dark fringes. The common wrong idea is that dark fringes are just shadows, places where no light is reaching. But Joe, this is completely, absolutely wrong.
Here is the crucial point, and I want you to remember this for your exams. Light from both the slits is reaching that dark spot. It is not an absence of light, it's a cancellation of light. Think about it. If you were to block one of the slits, that dark spot would instantly become bright. This proves that light was always reaching there. It was just being canceled out.
Excellent. So finally, let's just quickly connect this topic to the rest of the chapter and summarize everything we've learned today. This will keep it fresh in your mind for revision. Please remember, interference is not some isolated topic. It is built on the idea of coherence, which is a prerequisite. And it directly leads us to the next very important topic, diffraction. In fact, you can think of diffraction as a special kind of interference, just one that happens from countless tiny sources all packed closely together.
So, for your quick revision notes, here are the key takeaways. Number 1. Interference is all about the redistribution of light energy. 2. Path difference is the king. N lambda for bright, n plus 1/2 lambda for dark. 3. The fringe spacing formula is beta equals lambda d upon d. And 4. The most important one to remember, dark fringes are from the cancellation of light, not the absence of.
And with that, our soap bubble mystery is solved. That beautiful rainbow of colors is just interference in action. But this leaves us with a fascinating final question. We have seen what two slits do, but what kind of pattern does light create when it passes through just a single tiny slit? Well, that's a topic for our next explainer on diffraction. Until then, keep studying. All the best.